first example for the reverse arrow not being true. We take the sequence where xn is 1 over n, and then you would say, okay, that's a convergent sequence, right? It converges to 0. We said that before, so it must be a Cauchy sequence. Why would the other direction not be true? It's Cauchy, it's convergent. What is wrong? Well, I didn't give you the underlying set x yet. Let me be a little bit mean and say x is the set of real numbers without the point 0. So I'm intentionally removing the limit. That is mean, right? So you have your real line, but without the point 0. And then here comes your sequence. Here's 1, here's a half, here's a third, a quarter, fifth, and so on. And it's convergent to 0, but 0 is not an element of the space, so it's not convergent in this space. Still, it's a Cauchy sequence because, well, you could argue that the elements come closer and closer to one another, or you could be more clever, you could say this is, so xn is convergent in the whole of R. Okay, if you do not remove the point 0, then it is a convergent. Then it is a convergent sequence. So, by what we said before, it must be a Cauchy sequence. Xn is a Cauchy sequence, both in X or in R. In R, but also in X, because it's not using the point 0. I mean, right? I mean, none of these is equal to 0, so you could as well say it's a sequence in X. Okay, but it's not convergent. But xn is not convergent in X because the limit is missing. Okay, so you have this property, but you don't have this property, so you clearly cannot draw a conclusion in the other direction. This was the first example. You may call this a very exotic example because I was really mean. I mean, I was removing the limit. Let me take something else. Let me take x equal to the set of rational numbers. You know what that is? That is just a set of fractions, p divided by q, where p is running through the natural numbers and q is running through through all the integers. That is part of the real numbers, but it's of course not all of it. Okay, and now I take the following sequence. x1 is 3, or maybe 3.1. x2 is 3.14. x3 is 3.01. x4 is 3.1415, and so on. So xn is the n after comma digit approximation of the number p. So this converges to p, which however is not an element of Q, which is my space X. So again, this sequence is not convergent, the limit is missing. So is xn is not convergent in X, but in R. Because it's convergent in R, it is a Cauchy sequence in R, but it's only using values from X, because I'm only using rational numbers here, because I have fractions, or I have decimal expansions, which are just finitely many digits in R and X. So again, it's Cauchy but not convergent. So in a sense, the pattern is the same as in example A. The sequence is convergent, but unfortunately the limit is missing. So you could say, what a whole lot of rubbish. I mean, that guy is looking at convergent sequences and then intentionally removes the limit from the space. So here I was choosing the space X so that the limit is not in there. Here I was intentionally using a space that does not contain the limit. It's not the fault of the sequence. There's nothing wrong with the sequence 1 over n, and there's nothing wrong with this sequence. In a proper world, both of these sequences would converge, but unfortunately this world does not seem to be proper. Okay, this is not good, at least not for this sequence. The limit is missing, and this is not good for the sequence because the limit is missing. Instead of calling these improper or not good worlds, we have another word here. We say that a metric space X together with a metric D is called complete if every Cauchy sequence in X also converges in X. So in other words, if the reverse implication holds so that the two words convergent sequence and Cauchy sequence are actually the same. Okay, so they are then equivalent, but only if you're in a complete space, because we found out that it was not the fault of the sequence, it was the fault of the space. The space has holes, and because the space has a hole here, there are always sequences which fall in the hole. So the sequence stays outside the hole, but the limit is in it. So the sequence cannot converge, and it's totally not the fault of that sequence. Same here. Q has holes everywhere, and it's not the fault of the sequence, it's the fault of Q. It's not a complete metric space.